Thanks, Aaron. And also thanks to the organizers and the staff at IPAM for putting this all together. I really feel like I learned a lot over the last few days, and this was really helpful for me. But yeah, so I wanted to talk about this extension-theoretic approach to classification that I've been developing with Jose, Jamie, Aaron, and Stuart, that Jose and Kristen mentioned a bit about in their talks last week. And let me just start by, I'll recall the big classification theorem here. There is, Jose and Kristen talked a lot about some of the background of this and his historical development of it. So I'm not going to say a whole lot about that, but I also want to assume you remember their talks. But you have a sufficiently nice class of C-star algebras: separable, simple, nuclear, Z-stable, UCT. I'm assuming everything's unital here. It's not actually necessary. I think Weston's talking about a non-unital version in this afternoon. But for such algebras, they're isomorphic if and only if their Elliott invariant is isomorphic. I followed the notation others have been using and wrote this as KT. The Elliott invariant usually includes the positive cone on K0. In the simple Z-stable case, the positive cone doesn't give you any new information, and it also plays no role in the proof. So we chose just to get rid of it altogether, which is why the change in notation happened as well. And it's the second part that I want to talk more about is the classification of embeddings up to approximate unitary equivalence. That embeddings between such algebras, or even a bit more generally, are classified by K-theoretic and tracial data by this so-called total Elliott invariant. Right. And the key point is, as Jose outlined, the classification of morphisms implies classification of algebras. So it's really this part 2 is where all the work is. But let me say a little bit more about what this means. There's this compatibility condition I'm not going to write down. But the point is there's two sides of this: an existence and a uniqueness. The uniqueness portion, if you have two maps from A to B, if they agree on all the K-theory groups and all the traces, then they're approximately unitarily equivalent. The compatibility is irrelevant. There's the existence side, though, that you start with a map from all the various K-theory groups of A to the corresponding ones for B, and you ask, is there a homomorphism which implements all of these maps? The answer is usually no. What goes wrong is that you have various natural transformations between all of these groups. And the right statement is if you have maps on all the various K-theory groups which intertwine all the various natural transformations in the correct way, then it comes from a homomorphism. And that's what these compatibility conditions really mean. It's all the various natural ways of mapping the K-theory groups to each other. And any morphism is going to respect these natural transformations. So any map on K-theory you're trying to hit should as well. Okay, but these are two of the compatibility conditions, and there's a few more. Okay, so yeah, since one of the big themes of the conference was trying to extend these kind of classification results to an equivariance setting, I thought I'd talk a little bit about how you actually prove number 2, and the hope of, I think the proof we gave of this has a decent chance of extending to the equivariance setting, at least for group actions. I still don't really understand what an action of a tensor category is, but maybe even to that setting too. So I'm going to also throw in, I mentioned you can do this much more generally, like A doesn't have to be simple, B doesn't have to be nuclear, but I'm just going to assume both A and B are classifiable throughout. And I'm actually going to throw another assumption in that I want both of them to have unique trace for the talk. There's really two assumptions here. That there's at most one trace and at least one. In the traceless setting, it's actually a different game entirely. It comes down, everything's purely infinite in that case, and it's the Kirchberg-Phillips theorem. When there's several traces, the general outline's not very different than the unique trace setting. There's a different pile of machinery underlying a key point of the argument, but otherwise the outline's the same. So I'll just assume there's unique trace for everything. Okay. So start with some basic setup behind this. So the point is you're trying to describe all homomorphisms from A to B up to unitary equivalence. There's a standard intertwining, so it's an argument that's enough to describe approximate morphisms, A to B, up to a suitable notion of approximate unitary equivalence. I mean, this is a standard, right now, very well developed thing that goes, this has been around since like the early mid 90s, at least, in classification, that if you can describe the approximate homomorphisms, then you can describe all actual homomorphisms. Or equivalently, the way I prefer to, usually often these approximate homomorphisms are a sequence of UCP maps that preserve multiplication in the limit. I prefer to write it as a map from A into the ultrapower of B. So this is the C star ultrapower. So bounded sequences modulo operator norm null sequences. So classify this as up to, well, approximate unitary equivalence, and the ultrapower is the same as actual unitary equivalence. Okay. So that's what I'm actually going to talk about how to do, is classify maps into the ultrapower of a classifiable algebra. There's actually two kind of big payoffs to this. One is, of course, it's easier to build approximate multiplicative maps than actual multiplicative maps. But a somewhat more surprising one is, I've called this an extension-theoretic approach. B is simple, so B can't be written as an extension because there's no ideals. Simplicity is not preserved by ultrapowers. That B omega is actually not a simple C star algebra. And there's a key ideal inside of it that really drives the whole thing, and it's what gives you access to extension theory. So there is an ideal in B omega. There's actually several of them, but the most natural one. You have all B omega, so that, well, okay, so the trace on B induces a trace on the ultrapower just by limiting, taking the point trace pointwise and taking the limit. And then the null space of the trace is a two-sided ideal. I mean, that's true on every C star algebra, but the point is this is actually going to be a non-zero ideal, it turns out. And the easiest way to see it's non-zero is you can, if you rewrite this a little bit, you can show identify it with all bounded sequences in B, which converge strongly to zero, or two norm to zero, modulo the ones that converge in operator norm to zero. Of course, as soon as B is infinite dimensional, there's a lot of strongly null sequences that aren't norm uniformly null. But this is actually a huge algebra. And it has a remarkably nice quotient. If you think about what the quotient is going to be, it's, well, bounded sequences modulo two norm null sequences. So it's the two norm ultrapower of B, which is the same as if you take the two norm completion and then take the two norm ultrapower. So it's the von Neumann algebra generated by B and the GNS representation, the tracial ultrapower of that. So there's notation here that's been becoming standard in the C star algebra literature for the B using the lower omega for operator norm ultrapowers and the upper omega for the von Neumann algebra ultrapowers. I'll use that consistently. Although in this case, since I assume B is nuclear and there's a unique trace, this von Neumann algebra completion is just R. So this B omega actually has a relatively nice von Neumann algebra as a quotient. I mean, it maps onto R omega. And here's the extension that we're going to do all the extension theory with. It's often called the trace-kernel extension. Right. So this has been around for quite a while now. I think probably maybe slightly implicitly, the earliest form was Matui and Sato, and they showed strict comparison implies E-stability and under the appropriate assumptions. It was certainly very explicitly in the literature by 2014 or so when, but yeah, it's about 10 years old by now. But anyway, the point we're looking at is we're trying to understand morphisms from A into B omega. So I'm going to split B omega to two pieces like this, and we'll look at how A maps into the quotient, which is really a von Neumann algebraic problem, and how some kind of generalized map from A into this ideal, and then look at how they fit together. These generalized maps are going to be Kuhn's pairs, and which leads to KK theory. But you study maps from A into each piece and study how they fit together, and hopefully you get maps into B omega out of it. So strategy here. So classify morphisms from A into R omega. Classify all lifts of a fixed theta from A to R omega. So you have this lifting problem. And here's, this is via where all the KK theory and extension theory is going to appear. And there's one last step, which is you're going to get all kinds of various KK groups involving, this ideal J in part 2. You want to rephrase it in terms of something you can actually use, so you can do all these intertwining arguments and pull the whole thing back to A and B. So let's say compute the invariant in part 2. So this is, it's the last part is the only place UCT plays any role in this argument. When you actually try to take all this KK and X data and turn it into something reasonable. I probably won't say much of anything about part 3. I'll try to explain what's happening here in the second part. But, well, let me start with the first part, though. So the first part is actually where we've been saying there's von Neumann algebraic techniques that go into this. The biggest von Neumann algebra technique is right in this part 1, understanding maps from A to R omega. It's not even so much von Neumann algebra techniques as it is one von Neumann algebra results that we can just quote directly. So the point is, morphisms A to R omega, I'm assuming everything have unique trace, so this is necessarily trace preserving. I'm mapping it into a von Neumann algebra, so I may as well replace A with its von Neumann algebra completion. So Rn bijection with homomorphisms A, from the tracial completion of A to R omega. If A is nuclear, that tracial completion is R. So we're certainly an embedding of R into R omega, and it's unique up to unitary equivalence, I guess really by the Murray von Neumann classification theorem. So there's hence a unique embedding of A to R omega up to unitary equivalence. Right. So that Kahn's theorem gives you part 1. This is been used. I mean, you can even find these classification of maps from nuclear algebras to 2-1 factors in various forms in the literature. But it's always this proof. You just complete to a von Neumann algebra and apply the Kahn-Murray von Neumann classification. So that's that first part. You classify maps to von Neumann algebra. I want to point out, I said I think you could do a lot of this in the equivariant setting. You can imagine having group actions on everything, and you'd want to describe then something like all group equivariant morphisms from R to R omega up to the appropriate notion of equivalence. And presumably these Kahn, Jones, Akianu theorems can classify equivariant morphisms the same up to some notion of cocycle conjugacy the same way they classify group actions. I mean, there's probably things to check there, and it might even be, I don't know exactly what's known, but it's definitely within the realm of possibility that, the theorems in the equivariant setting are already done at the von Neumann algebra side. So it's the second part that is a bit more where a lot of the work is. So there's really, so fix theta as above. It turns out all these lifting questions are independent of how you chose theta, but let's just choose a theta and go from there. So you have this extension again. You fix the map theta, and you want to decide what the lifts of theta look like. And this comes in really two parts. So maybe I'll call part 2A an existence of a lift. Is there any lift of theta at all? The answer is often no. If B is projectionless and A has a lot of projections, there's just not going to be any morphism from A to B omega, much, even ignoring theta. So at the very least, there's K-theoretic obstructions. I mean, there's obstructions on K0 and maybe more complicated things. So the most general obstruction you can write down here is an X element. I have an obstruction, which I'll just call E in X, A, J, B. So I'm really playing it fast and loose with separability now and also with units, but just ignore that. So the way that this extension comes from is I can take the pullback extension here. So E is just the preimage of A under the quotient map, Q inverse of theta of A. So that maps onto A by the restriction of Q. The kernel is still JB, and all the unlabeled arrows are just inclusions. And that extension on the top is the extension that gives you this X element. Right. Now, it turns out the way this is set up, you can think of this sort of an analogy with BDF theory, where that's J would be the compacts. Maybe this is B of H in the Culkin algebra. So you get this X group, which determines lifts. So the thing you get pretty much for free from definitions is if theta does lift, this X element vanishes. The thing you really want is a converse. If this X element vanishes, does theta have a lift? That doesn't come for free. What you do get roughly from definitions, and I'm going to be a bit imprecise with this, is you can't lift theta directly, but you can find some slightly large, you can dilate to a larger extension. You have a map A, which is theta direct sum something else. into the quotient. So that direct sum lifts so that theta 0, 0 pi lift and the 2, 2 corner pi both lift to star homomorphisms. So that's sort of what you get by unwinding the definition of X. I mean, what you're trying to do is turn all such lifting problems into an abelian group, and then just by additions, direct sum, and then whatever group relations follow. But because the group has cancellation, you're forcing cancellation, you're getting this kind of stuff. That being the zero element doesn't mean you had a lift. It means you're somehow stably equivalent to something which had a lift in this sense. Now, the key thing that drives this, and here's a suitable version of Wojciechowski's theorem, which is where all the hypotheses start to appear, except amenability. That you get enough conditions on this J that you can start to cancel that pi. I mean, it's just like in classical Brown-Douglas-Fillmore theory, the deepest result about the whole thing is that two essential extension, homotopy invariance, I guess, is really difficult too, but one of the deep results at least is that two extensions, essential trivial extensions, are always unitarily equivalent. You need some analog of that. I mean, that's not literally true here, but some form of it will tell you that this theta plus pi is somehow equivalent to theta. So in some sense, and in some sense, which preserves liftability. So since theta plus pi lifts, you would get that theta also lifts. If you can somehow absorb the pi back into theta by some Wojciechowski type absorption theorem. So in the end, there exists a psi from A to B omega, if and only if some element in X vanishes. So there's this purely homological obstruction to lifting. So I'm nearly out of time here. Let me just, there's the second part is once you have at least one lift, you want to somehow, can you describe all possible lifts or all possible morphisms from A to B omega? And they'll just write down what the answer comes out to be. So given, once you can produce a morphism from A to B omega, it turns out that the set of all morphisms from A to B omega up to unitary equivalence is actually a group. I mean, it can't quite canonically be a group because there's, a group has the special element 0, and this is somehow too homogeneous that there's no distinguished representation to play the role of the identity. But I don't even know don't know quite what the right word is, but once you pick what you want to be 0, it becomes a group. So it's in bijection with the group KK of A, JB, where basically psi is the chosen lift psi is what gets sent to 0. And you can think of this roughly as being phi minus psi. That takes some interpretation, and even then there's a lot of well-definedness issues, but it turns out you get such a bijection. The word is torsor. Thanks, Andre. Okay. So it's but yeah, so you get this two-step classification. There's an obstruction to having at least one morphism, assuming it vanishes. All the morphisms are indexed by this KK group. So this part 3 was a matter of computing these two things. And it's at this point, if you write out all the computations, assuming you have UCT, write out what the UCT says you, and just start computing by chasing around the 6-term exact sequence. this total invariant I wrote down at the beginning is what falls out of the computation. And all the compatibility maps are essentially the maps in this long exact sequence. So it's the total invariant just comes out of the computation at the very end. But what I want to mention for the equivariance setting, so I think the von Neumann algebras, that part one is almost entirely done. Maybe just you have to reword Okeanu's theorem a little bit. Part three, I don't have a good feeling for what the invariant is, but it's if you throw some kind of equivariant UCT at it, it should just be some computation, and whatever falls out will fall out. So it's the second part that really has to be done in the equivariant setting still. It's in this non-equivariant setting, it's about the same order of magnitude as the Kirchberg-Phillips theorem, and it uses a lot of the same preliminary results. I think the fact that Gabor announced that earlier that Gabor and Jamie now have an equivariant Kirchberg-Phillips theorem. This might not actually be so far away from just being able to run this proof in an equivariant setting. I mean, there's things that need to be done, but we might be within a few years of seeing it in a full-scale equivariant classification results. But okay, so I'm out of time. I'll stop with that. But thank you.